A very simple but also remarkably useful algorithm is copy, shown here on slide 9. Copy simply copies the elements from some source range from the begin up to but not including the end iterators in some container. That is the B and E shown here as the first two arguments. And those are copied into elements in an output container starting at the location B out. Now, of course, B out could be an ordinary iterator or it could be an inserter. Here we're setting up a vector of int V containing 13579 and an empty deck of double D, and I'm copying from the vector into the deck of doubles D by using a back inserter. Now notice that a type conversion does occur here. D is a deck of double in this case, whereas V is a vector of int. But this is fine because when you use pushback of an int into a container that's expecting a double, the conversion from int to double will simply happen automatically. Following the copy, I'm using a range for loop to display what's currently in D. What comes out is 13579. Now actually these are doubles, but recall that the default display of a double does not show anything for a trailing zero. Front inserters, shown here on slide 10 with a little example program on slide 11, are basically the same as back inserters, except that a front inserter uses the push front member function to push a value at the front of a container rather than push back. We have the same awful notation if we want the full-blown description of the front insert iterator type, but nobody wants to type that, so what we use instead is auto with front inserter on some container to provide the initial value of our insert iterator, our front inserter IT2. Here on slide 11, I have V as a vector of int, 13579. I have D as a deck of int that is currently empty, and I'm using copy with back inserter, first of all, to copy all of the elements from V and push them one by one onto the back of D. So when I display the contents of D at this point, what I'll see is shown on slide 12 is 13579. No surprise. But in the green copy algorithm, I'm using front inserter instead to specify where I want values inserted into D. So this time, when I copy the elements from V, from begin up to but not including end, each of those values is going to be pushed on the front of D. The values that D already contained are still there, and so when I display D now in this second range for loop, I still have the 13579 that I had from the first copy algorithm, but now I've got 97531 inserted ahead of what had been in D. Now, the terminology regarding insert iterators is a little bit confusing, potentially, in much the same way that when we talk about compiling a program, what we really mean is pre-processing the code, then running the code through the compiler to create object code, then assembling those object code files together using a linker to get an executable program. We tend to use the word compiler to mean all three of those phases. Insert iterator is a category that includes front insert iterators, back insert iterators, and general insert iterators. However, the term general is not part of the standard description of the language. So in Josudas's C++ standard library book, he makes use of the term general insert iterator to differentiate this kind of insert iterator from the front inserters and back inserters. The difference is that a general insert iterator uses the insert member function to insert a value into a container, as opposed to push front that pushes a value onto the front of the container, or push back that pushes a value onto the back of the container. Now the insert member function needs to be given a position, which is an iterator specifying where you want that new value to be placed. And this in turn creates a little bit of an oddity for associative or tree structure containers and for unordered or hash table containers. Associative containers and unordered containers maintain their own rules about where new values are supposed to be positioned. So they do, for consistency with the sequence containers, provide a member function named insert that takes both a value and a position, but the position is only treated as a hint or a suggestion about where the new value might be placed. It's actually up to the container itself to definitely decide where the new value is going to be positioned. Now it turns out that the insert member function does return the actual position, that is an iterator for where the inserted value was actually placed. Okay, so let's see some examples of general inserters. First of all, we have the usual declaration notation here on slide 15. You can either type out the full-blown type description, insert iterator with the container type in angle brackets, or much more commonly use auto and create an inserter for some container starting at some initial position. Now the initial position, here we're calling it pose 2, might be the end of the container, might be the begin of the container, might be somewhere in the middle of the container, depending on what kind of container you're working with. Now in the case of front inserters and back inserters, we saw that star of the inserter actually did nothing. Likewise, increment of the inserter, whether it was a post increment or a pre-increment, does nothing. And then the notation inserter equals value was interpreted either as container dot push back of some value or container dot push front of some value. But in the case of a general inserter, saying iterator gets value does an insert at the specified position of some value. And then insert returns to me the actual position where the value was inserted, and the assignment also causes an increment of that position to be performed. Okay? So if IT is a general inserter, when I say IT gets val, that first causes the container's insert member function to be called with the value and the position that you specify. That returns the new position or the actual position where the value was inserted, and that position iterator is incremented automatically. Let's walk through some examples of this. Here we have a couple of general inserters that we're using in the code on slide 17. In this example, I have the vector of int v initialized with 471349. I have a dec of int d, which is initially empty, and a set of int s, which is initially empty. In the first copy algorithm, the red copy algorithm, I'm copying all the elements starting from v.begin up to but not including v.end, using an inserter that will use the insert member function of the dec to insert a value at the end of the dec. Now, let's understand what's going on with this inserter. In the first iteration within the copy algorithm, 4 is going to be inserted where that inserter specifies. That is, we're going to end up invoking, if we look back over here on slide 16, we're going to end up invoking d.insert with a value of 4 and a position of d.end. So 4 will be inserted ahead of the end, which means it will become the new final element in the dec, and what I will get back is the position of that final element. Now, because we did the insert, the end has moved one place to the right. The position that we get is no longer the end. The position that we get is an iterator for the final element that is actually within the dec. But notice that I also do a plus plus pose, which causes the position to be the end once again.